Hey guys, welcome to question 2 and 3 for the level 2 waves. Okay, so for this is 2018. Okay, so we'll get straight into it. Question 2. Later, Sophie shines a green laser beam from air into a glass of juice. When she does, she notices that the light refracts. Velocity of light in air is 3 times 10 to the power of 8 meters per second. The refractive index of air is 1. The refractive index of juice is 1.34. Define refraction. Simply, we're just gonna say refraction. Refraction is the bending of waves when it passes through one medium to another. Okay. Okay, so basically refraction is the bending of waves when it passes from one medium to another. And that's going to get you the achieved grade here for the correct definition. Okay, B. The diagram below shows the cross-section of the glass looking down from above, with the juice inside. For the purpose of this question, you can assume the glass itself is very thin and it has a negligible effect on the path of the light rays. Complete the diagram clearly showing the refraction of the light ray as it enters the juice. Okay, so simply, so as the question tells us, the refractive index of air is 1 and the refractive index of juice is 1.34. Therefore, we can infer that the juice is more dense than air. And that means when the wave is going to be passing from the air into the juice, it's going to slow down because the juice is more dense. Okay, so it's traveling from a less dense medium to a more dense medium. So therefore, the wave will start slowing down. Okay, and when it slows down, it's going to be bending towards the normal. Okay, so therefore we're going to draw our refracted ray. Okay, our refracted ray is going to bend towards our normal. It should look something like this. Okay, should be bent towards the normal. Okay, so in this question you have to make sure that the angle of refraction, that's this angle, so angle of refraction. So angle of refraction must be bigger. Not bigger. It must be smaller than angle of incidence. Okay. Right. So so calculate the angle of refraction. Okay, so basically we're going to be using our Snooks law. The Snooks law is n1 sine theta 1 equals to n2 sine theta 2. Okay, so it tells us the refractive index of air is 1 and the refractive index of juice is 1.34. Because we start our ray starts in the air and moves into the juice, we can say that our initial refractive index was 1. Okay, and our initial angle of incidence, okay, that's this angle here, that's this angle here. Okay, so this angle here is 28 degrees. Okay, and that's the angle that it makes is it 28? Yeah, 28 degrees, and that's the angle that the normal makes of the ray. Okay, so the angle that the normal makes of the ray is the angle of incidence. Okay, and so therefore we can say that one sine of 28 equals to n2, which is our refractive index of our juice, which is 1.34. 1.34 sine theta 2, we don't know. Okay, so we're going to say that sine 28 divided by 1.34 equals to sine theta 2. Okay, and therefore we'll say that sine inverse of sine, sine 28 divided by 1.34 equals to sine theta, not sine theta, so just equals to theta 2. Therefore, our theta 2 should equal to 20.5 degrees. Okay. So basically, we can say that our getting both the diagram correct and the correct calculation will get you a merit grade. Okay, so correct diagram and correct calculation get you a merit grade. To get an achieved grade, it's either getting the correct diagram or the correct calculation. Okay, so either one of the two will get you the achieved grade here. All right, moving on. When the light hits the side of the glass as shown to the right, the ray bounces back inside. Under what condition will the ray bounce back as shown in the diagram? So as you can see, our initial ray, so our incident ray, our incident ray is going through the orange juice, is hitting the barrier with the air and orange juice and air barrier, and it reflects back into the orange juice. This is called total internal reflection, okay, which means that the ray bends so much that it bends right back into the orange juice, okay. So we know that this only happens when the angle of incidence is greater than our critical angle. So if we have our critical angle, means that the ray will bounce off 90 degrees, okay, 90 degrees to the normal, okay. However, with the total internal reflection, that means our angle of incidence must be larger than our critical angle. And we can also say that this can only occur if we're moving from a more dense medium to a less dense medium. So that's only when the ray is bending away from the normal. Okay, so that's only when we're traveling from a more dense medium to a less dense medium. Okay, so we're gonna say that under what condition? Okay, so we're gonna say our angle of incidence is greater than a critical angle. Incidence is greater than the critical angle. Okay, and we can also say that we're moving from a more dense medium to a less dense medium. Okay, getting your correct statement here, okay, that'll get you an achieved grade. Okay, but it's also linked in with it also links back to part 2. Okay, so part 2. Calculate the minimum angle at which the light has to hit the side of the glass for this effect to occur. Okay, so the minimum angle. Okay, so that's basically calculating our critical angle. Okay, so the minimum angle, so which the light has to hit the side of the glass. That's basically calculating how much does the angle of incidence have to be in order for the ray to refract at 90 degrees to the normal. Okay, that's not very good drawing. 90 degrees from the normal. Okay, so how high does the angle of incidence have to be? Simply we'll say that Snook's law, n1 sine theta 1 equals to n2 sine theta 2. Okay, our n1, okay, we're starting in the orange juice this time, so it's at 1.34 sine theta 1. We don't know our angle of incidence. And n2, we're traveling into the air, so therefore therefore the refractive index is 1 sine 90. Okay, we say sine 90 because the ray travels 90 degrees to the normal. Okay, so therefore we can say that sine theta 1 equals to 1 divided by 1.34. Therefore theta 1 equals to inverse sine of 1 divided by 1.34. If you plug this into a calculator, you should get to your angle of incidence equals to 48.3 degrees. Okay, so getting your correct statement, okay, plus your correct calculation will get you a merit grade. But just getting one of these, okay, so just any one of these will get you an achieved. Okay, so any individual one will get you an achieved. Okay. The green laser used in this experiment has a frequency of 5.6 times 10 to the power 14 Hz in the air. By first calculating the wavelength of the laser in the air, calculate the wavelength of the light rays in the juice. Okay, so as stated on the first page, our velocity of the light in air is 3 times 10 to the power 8 meters per second. Okay, so therefore it has a frequency of 5.6 times 10 to the power 14 Hz in air. Okay, so therefore we're going to say that our velocity equals to f lambda. Okay, our velocity is 3 times 10 to the power 8 equals to 5.6 times 10 to the power 14 lambda. Okay, if we plug this into our calculator, okay, so that's basically 3 times 10 to the power 3 times 10 to the power of 8 divided by 5.6 times 10 to the power 14. Okay, so that gives you that our lambda comes out to be 5.36 times 10 to the power of negative 7. Wait, just let me double check that. So Yeah, that should be the correct 5.36 times 10 to the power of -7. Okay. So now we have to calculate the wavelength of light rays in the juice. Okay. So basically, we know that we're going to use the equation that n1 over n2 equals to lambda1 over lambda2. Okay. So our initial refractive index over our new refractive index equals to our original lambda over our new lambda. Okay. So therefore we are. Okay, so our wavelength of the light rays in the juice. So our wavelength of the laser in the air is 5.36 times 10 to the power of -7. Okay, and that divided by an unknown wavelength, so lambda 2 equals to, we have our refractive index of 1 in our air, and we have our refractive index of 1.34 in our juice. Okay, so therefore lambda 2 equals to 5.36 times 10 to the power of -7 times 1.34. Okay. Oh no, it's the other way around. Sorry, it's the other way around. Sorry, it's lambda 2 over lambda 1. Just check. It's lambda 2 over lambda 1. Yeah, apologize for that. So it's basically just the other way around. Apologize for that. So we have our 1 divided by 1.34, and that equals to our lambda 2 we don't know, divided by our lambda 1, which is 5.36 times 10 to the power of -7. Therefore, our lambda 2 equals to 5.36 times 10 to the power of -7 divided by 1.34. Therefore, your lambda 2 should come out as 4 times 10 to the power of -7 meters. Okay, and and this is linked to part II. Okay, so explain why the wavelength of the green laser in the juice is different from its wavelength in air. Okay, so basically, the wavelength is different because it has a different medium. Okay, so when we have our laser in the juice, because it's a more dense medium, okay, the wave is traveling slower in the juice, and it's traveling faster in the air. Because frequency remains the same in both cases, we can say that our v is proportional to our lambda. Okay. So if our v goes down, then our lambda will also go down, and if our velocity goes up, our lambda will also go up. Okay, so we'll simply say that because frequency is constant, okay, we'll say that v equals to f lambda. Okay, and therefore v is proportional to lambda. In the juice, it is more dense, hence the waves are traveling. Slower, slower than in air, and hence a lower lambda. Okay, we'll say that in air the wave is traveling faster. Okay, it's traveling faster, hence lambda will also be larger. Okay, so basically you're gonna say that the frequency is constant, v equals to f lambda. Okay, and v is proportional to lambda. So you say in the juice it's more dense. Okay, because it's more dense, your velocity is smaller, and because your velocity is smaller, your lambda will also be smaller. So and in the in the air, your waves will be traveling faster, and because it's traveling faster, your lambda will also be higher. Okay. So to get your excellence grade here, you have your calculation correct. So that's your 4 times 10 to the power of -7 meters, and you have your explanation correct. Okay, that will get you your excellence grade. Okay, to get a merit grade, you're looking at either one of these. Okay, so these are worth merit grades on its own. Okay, so merit plus merit gets you the excellence. Any one of these correct will get you the merit grade independently. And to get an achieved grade, you're only finding the correct wavelength in the juice, okay? So correct, sorry, not in the juice, in the air, okay? If you find the correct wavelength in the air, that'll get you an achieve. Okay, moving on. Question 3, radio and light waves. Sophie decided to investigate the difference between AM and FM waves. She knew that both are radio waves that travel at 3 times 10 to the power of 8 meters per second and can travel extremely large distances. An important difference she discovered was the size of their wavelengths. Sophie's favorite AM radio station transmitted waves with a wavelength of 550 meters, whereas her favorite FM station transmitted waves with a 3.3 meter wavelength. Wavelength and lambda and the amplitude A are properties of these waves. On the diagram below, mark the wavelength and the amplitude. Okay, so we know that the wavelength is the difference between two crests or two troughs, okay? And our amplitude, okay, is how high the maximum displacement and our minimum displacement, okay? So we can say that our wavelength is the difference between two wave troughs or two wave crests, okay? So we can say the difference between the two wave troughs here that give us our lambda. And we can say that the size of our maximum displacement or the size of our negative displacement will give us our amplitude, okay? So basically we can say that from the top of the wave to the horizontal axis, that will give us our amplitude, okay? So this line here will give us our amplitude, okay? So if we have also to mark our wavelength and our amplitude correctly marked, I'll get you an achieved grade here. Right? At home, Sophie's radio could detect one of the radio stations, even though a hill was between her house and the transmitter. This can be modeled using the diagram below. So as you can see, there's the traveling radio waves and there's a barrier. The barrier is the hill, okay? So the waves are going to hit the hill, okay? The traveling radio waves, they're going to travel in a straight line. They're going to hit the hill, and because it hits the obstacle, it's going to begin to diffract, okay? And when it diffracts, it will bend, and because it bends, it can bend towards the house, and hence Sophie can hear the radio station. Oh, sorry, just get rid of this. Not duplicate, delete, sorry. Alright, so we have our name this phenomenon that allows us to happen and state whether the AM or FM station is more likely to be detected at the house. Give a reason for your answer. So basically, we can say that when the waves hit the hill, the diffraction will occur. And basically, the AM station had a very large wavelength, and because it has a very large wavelength, okay, it is able to diffract more. And while the FM station has an extremely low wavelength and is not able to diffract as much. Okay, so simply we're gonna say, we're gonna say that diffraction occurs. Okay, so when the waves hit the hill, they will diffract and bend towards the hill, and not bend towards the house. Okay, so we'll say that the AM station has the extremely large wavelength. Has a large wavelength and hence is able to bend more. The FM station, the FM has a low wavelength and hence bends less. And then you say hence the AM station is likely to be detected. Okay, so if you're able to say that, so you're going to say that the phenomenon is called diffraction, and you're going to say that the AM station has an extremely large wavelength and is able to bend more, while the FM station has the extremely low wavelength and is bending less. Getting both of these points will get you the merit grade, okay? While getting diffraction, okay, diffraction will get you an achieve. So if you're mentioning diffraction, that will get you the achieved grade. To listen to our other favorite radio station, so if we used a fiber optic cable internet connection, the music is encoded as light pulses which are either on or off. To show what happens when these two pulses are sent through the fiber optic cables in opposite directions, a simplified diagram is presented below. Each pulse travels 3 squares horizontally every time period. Draw the resulting superposition after one time period on the diagram below. So one important point to note, okay, the question tells us that each pulse travels 3 squares horizontally each time period, okay? So ignore this. So we had our original wave here. We're gonna just mark over dotted line. So we have our original wave here, and we also had our original wave here. So after one time period, each square would move 3 units. Okay. So this new square would be 1, 2, 3 would be here now, and this square here, okay, it would be 1, 2, 3. So this point will be here, this point 1, 2, 3, so it will be here. So therefore this wave would be here. Okay, so now because this is they're in phase, the two waves are in phase, therefore there will be the constructive interference, and because there is a constructive interference, we can say that they stack up. Okay, so the waves stack on top of each other, and therefore it will create one bigger wave. Okay, so simply say that originally we had waves here, so therefore this part here will stack on top of the okay, so therefore our final wave should look something like this. Okay, so therefore this will be our final produced image, and to get this correct produced image, okay, that will get you the Americ grade. Okay, to get an achieved grade, to get an achieved grade, is you're either off by 1 square. So for example, if you drew your picture here, for example, if you draw your pulse here, for example, you will get an achieved grade. Okay, but to get the merit grade, you can't make any mistakes. Okay, so this is your merit diagram here. All right, final question. Okay, so in another place, so if you just try to make the radio signal stronger by using 2 FM transmitting aerials, A and B, placed 6.6 meters apart. Sophie needs to know where the resultant signal will be the strongest or weakest. On the diagram below, not the scale, mark 1 point where the resultant signal will be extremely strong, mark which is a maximum, mark it as X, and where would the strength of the signal will be a minimum, mark it as Y. Comprehensively explain why these points result in different signal strengths. Okay, I'm just going to remove this. So basically we're trying to detect our nodal lines and our antinodal lines. Okay, so our antinodal line occurs when 2 troughs meet each other and constructively interfere, or when 2 wave crests meet each other and they constructively interfere. Okay, so simply we'll find 2 places where both wave troughs or wave crests interfere. So we can simply say, for example, our center axes here, this will all be constructive interference. Okay, so just pick any one random point. Okay, we'll say this point, we'll mark it as X, and we'll try to find one where a signal will be a minimum. So that's when a wave crest is overlapping with a wave trough. Okay, so we're gonna look for when a wave trough of the red circle meets with a wave trough of a green circle, for example. Okay, so for example, we're going to say this point here. Sorry, not that. So this point here, that is point Y, because the crest of wave of the red circle is overlapping with the wave trough of the green circle. Okay, so therefore that will be the destructive interference, and therefore the waves will cancel each other out. Okay, so simply we'll say our point X. Okay, we'll say our point X lies on the central maxima, and hence both wave crests overlap. Both wave crests overlap and cause the constructive interference. Okay, so we're going to say that the we're going to say that the path difference is 1 lambda. Therefore, constructive interference and the waves add to create a strong signal. Okay, so that's what we're going to say, okay? So basically, we're going to say that our path difference is, well, not necessarily 1 lambda, but we're going to say that's a whole number, okay? So we're going to say that our path difference could be an n lambda, okay? Not necessarily 1 lambda, but an n amount of lambda, okay? So it's a whole number, so therefore there's constructive interference, okay? And therefore the waves add up to create a strong signal. At point y, okay, at point y, the point y is situated at a nodal line, and this means that a wave crest is meeting with a wave trough. It's meeting with a wave trough from the other source. Okay, we're gonna say that the path difference is only half of it's only n minus 1/2 of lambda, and therefore there will be a destructive interference. And the waves cancel each other out. To produce a weak signal. And that will be your final answer here, okay? So therefore, we're going to say that to get excellence, you need to describe that the point X or Y is situated on the central maxima, and that's when the both wave crests overlap, okay? You're going to explain what the path difference is, okay? So you're going to explain what the path difference is, and because of this path difference, what type of interference it will be. Okay, that's the same for point Y. So the point is, for example, at a nodal or an antinodal line, okay? So you're going to be explaining, okay, you explain that the path difference and what this path difference means in terms of what type of interference. And because of this interference, what will happen as a result, okay? So, and that will get you your excellence grade, okay? So to get both of these, will get you your excellence grade. To get a merit grade, you're looking at X and Y marked correctly. So you mark your Y correctly, you mark your X correctly, and you have 2 correct explanations, okay? So you could be explaining, for example, point X is on a central maxima, a node or an antinode, or you're going to say just any 2 points that I mentioned before will get you a merit grade, okay? And to get an achieved grade, you have your X or Y marked correctly and only 1 explanation correct. So basically just 1 point will get you the achieved grade. Alright, thank you for watching this video. I hope you enjoyed the video. If you have any comments, feel free to leave it down in the comments below. If you have, please leave the video a like if you enjoyed the video. And I'll see you all in the next one. Thank you.